All right.
Mr. Stanley, where do those get posted? Because I haven't seen like a link where it says Zoom meetings posted here on any of my classes, but all my classes say they record them and post them, but I've never seen them.
So I'm posting mine underneath the notes that they go with. So like underneath the notes that we go over today, I'll go back in and add in this video so that it goes with the notes. If you want, I can also make a section of just the Zoom classes and videos if you think that'd be easier for people to find.
I think it would be easier.
All right, well, that's
Because
good to know.
I'm gonna suggest that as well to Miss Jones, because I'm
Awesome.
having that problem with her. Um, and it's just to go back and review notes because I try really hard to
Right.
be in y'all's classes.
Mm-hmm.
Um, but it helps with, English 3 and IPC because those are very hands-on classes, just like my other
Yeah.
course, economics. Like
Oh, for
they're
sure.
very note written
Mm-hmm.
classes. So
Yeah. All right. Yeah, that's a good idea. Then I'll suggest that to the other teachers too, is to have a place on the Google Classroom just for the Zoom recordings to live. Good call. All right. So hopefully today shouldn't be too crazy note intensive. So we're going to be going over something that you guys maybe already kind of sort of have an idea about or understand a little bit. Let's see. All right, let me make sure I can see everybody who's here. Oh, that's not what I wanted. Okay, man, this Zoom recording is real wacky. All right, there we go. So if you look under week 2, our Tuesday notes for today have actually been broken up into 2 parts. One that will go with the assignment that's due today that a couple people have already completed. And the second part of the notes will go with the assignment that is going to be due on Wednesday. And so I'm going over 2 notes today, one specifically for the assignment today, and one that covers stuff that your Wednesday assignment will be about. So let's go ahead and jump into these notes, all about states of matter and phase changes. So what are our major states of matter? What are some of their specific properties? And how can we switch between one state and another? That's what the first section of this notes is going to go over. All right. So first part of this is states of matter. We're going to talk a little bit about something called the kinetic molecular theory, which basically just kind of describes how these different states operate. And then we'll talk in detail about each one of the states of matter. These are things that you've probably heard of before and have a little bit of an understanding about. Today, we're just going to be going into a little bit more detail. So starting off with what's called the kinetic molecular theory, which is a very big, scientific, confusing sounding name, but it really describes something very, very basic and very simple. So the kinetic molecular theory, or KMT, as I'll sometimes call it, is this idea that tiny, constantly moving particles make up all matter in the universe. So matter is just a fancy science word for stuff. That's what it means. You're matter, I'm matter, this table is matter, the air around us is matter, the water coming out of your water faucet is matter. Everything in the universe is matter. And the KMT says that all of this matter, if you look down at teeny, teeny, tiny, super microscopic size, it's all made of tiny little particles that we'll talk about later on in the year here. And these particles are constantly moving and shifting around. Sometimes they're shifting around a whole lot. Sometimes they're barely shifting around at all. So the way that you can get these particles to shift around faster and faster and faster is to increase the temperature of your matter. There we go. So as the speed of these particles goes up, that means the temperature is going up as well. So these tiny particles are moving. The hotter it gets, the faster they move around one another. So that's all the KMT says. Like I said, it sounds big and complicated, but it's basically just saying tiny particles are what make up everything in the universe. And as the temperature of matter, of stuff, increases, those tiny particles move faster and faster. So today, one of the things that we're going to talk about is in the different states of matter, those being solids, liquids, and gases, what are these particles doing when we're talking about a solid versus a gas versus a liquid? So our three states of matter starts with solids. This computer, this table, this chair that I'm sitting in, the bones and muscles in your body, all of these are solids. Solids have a low kinetic energy. So that's what this Ke stands for right here, is kinetic energy. And that's basically just like what we were talking about earlier with the particle speed. So in solids, we've got a really low kinetic energy. The particles vibrate, so they can sort of move in place a little bit, kind of like what my mouse cursor is doing right now, but they can't really move around, right? And this makes sense because in solids like wood and concrete and ice, stuff is stuck in place, right? The table that my computer is sitting on isn't going to start washing back and forth all of a sudden because it's a solid. Its particles are stuck together, stuck in place. So because they're stuck, they don't have a lot of motion. So we call that low kinetic energy, low Ke. The other thing about solids is that they have what's called a definite shape and volume, meaning that the amount of space that they take up, the amount of space that they take up and their shape, what they look like, always stays the same. So like if I take this pen here, this pen is always going to take up the same amount of room in the air, or if I put it in a cup, or if I drop it on my computer or drop it on the ground like I have just done, it's always going to say pen shaped and pen sized. It's not going to change what it looks like, even if you change where you put it in the room. That's what we mean by definite shape and volume. That means it's set, it's permanent, it's not going to change. So that's solids. Low energy, low movement of the particles. They're basically all kind of stuck together. And yeah, maybe they like vibrate a little bit by one another, but that's about it. They're basically staying in place. So our next state of matter, if we add in a little bit of energy to our solids, we can turn them into liquids. So liquids have a higher kinetic energy than solids, right? If you think about a liquid like water, there's a lot more motion going on there. So the particles move around a lot more than in solids, but they don't completely like separate out from one another, right? They stay pretty close to each other. They just can kind of move all around each other really easily. So a lot more motion than solids with their particles, which is why we have this higher energy. But their particles still stay kind of close with each other. Liquids have an indefinite shape, right? You can't describe what shape that water is in. Like you can't say water is a square or a rectangle because it'll make the shape of wherever you put it. If you have like a little glass, you pour the water in there and now the water looks round. If you pour that into like a little square cup or a square Tupperware container, then the water is going to fill up that square. So the shape of the water depends on whatever you put it in. And this is true for all liquids. They'll take the shape of whatever container that they're in. They do not have a set shape. They have an indefinite shape. It's not defined at all. But liquids still have a definite volume. So, for example, if you take a cup of water and you pour that into a glass for drinking, but then you pour that into a big container, that like a pot on the stove, and then you take that and you pour it back into your glass, it's always going to be 1 cup of water. The volume of the liquid doesn't change based on where you put it. It just changes how it looks. If you put it in a square Tupperware, it's going to take up that square. If you pour it into a big circular pot, it's going to fill up that pot in a circle. So the particles are more spread around. They're filling up the shape wherever they are, but they can't change how much space they take up. They're always going to take up 1 cup if you started off with 1 cup. So liquids, more energy than solids, don't have a set shape, but they do have a set volume. And then lastly, if you're following along, you might be able to guess that if we started with solids and we're going to liquids, our next state of matter and the last one that we're going to focus on today are gases. So gases have the highest kinetic energy out of these 3, right? They have very fast moving particles that can separate and move all around the room, the air, wherever you are. These gas particles are spread out and moving fast. So they have the highest kinetic energy. They're speeding around all around you. Gases are really interesting because they do not have a set shape or a set volume. Gases can take up more room or less room in an area depending on all sorts of different factors, including things like temperature. So gases get a lot more dense when they get cold, they get a lot smaller, and they get a lot larger when they get hot. So if you think of like a balloon, right, that you get at a kid's birthday party or something, if you take that balloon and you stick it in the fridge for a day, when you pull it out a day later, that balloon has shrunk and gotten really, really small. That's not because a whole bunch of air escaped and left the balloon. That's because the gas inside got smaller, its volume got smaller because it got cold. So gases fill up whatever container they're in, and their volume can get bigger or smaller depending on the container and the temperature and the pressure, stuff like that. So we have super fast particle motion all throughout our container. We've got these particles bouncing off the wall all around here, moving super fast, very spread out from each other, and getting bigger or smaller depending on the container that they're in and how hot or cold or how much pressure there is around them. So solids, low energy, very compact and tight together, set shape and volume. Liquids, medium energy, can move around each other, don't have a set shape, they just fill up wherever you put them, but they do have a set volume. And then our gases are our highest energy, particles zooming around all over the place, super spread out from one another, and can make their shape and their volume change depending on the temperature and the conditions that they are in. So solids and liquids and gases do not stay solids, liquids, and gases for their entire life. They can change between one another. So you can take a solid, turn it into a liquid, turn that into a gas, turn that gas into a liquid, and turn that liquid into a solid. When you do that, you go through something called a phase change. And so today, we're going to focus mostly on what is it called when you change from one phase to another. So these first couple you guys are probably familiar with. So we have melting, which is where when you go from a solid to a liquid. So you take some ice, set it out in a glass on the counter for a couple hours. It's going to melt and go from solid ice to liquid water. If you go the other way, you have what's called freezing. So you take something liquid, cool it down, those particles lose some of their movement, come together and clump up and make a solid. So solid to liquid is melting, liquid to solid is freezing. So these happen at a certain temperature called the melting point or the freezing point. So for water, it's at 0 degrees Celsius or 32 degrees Fahrenheit. If you take a block of ice and slowly heat it up, after it passes 0 degrees Celsius, it'll start melting and turning into water. Similarly, if you take a whole bunch of water, stick it in the freezer where the temperature is below 0 degrees Celsius, then that liquid water will start freezing and eventually turn into a solid. So the temperature where this happens is called either the melting or the freezing point, depending on which direction you're going in, essentially. We can also change from liquid to gas. So there's actually two ways that we can change from liquid to gas. There's the fast way and the slow way. The fast way is called vaporization. And when we talk about water, we talk about water boiling, right? You're getting ready to make some pasta, you put the water on the stove and crank up the heat. After about 5 or 6 minutes, if you got a big pot, you'll start seeing little bubbles forming in the water and escaping into the air as steam. That's when we have liquid water changing to gas, water vapor, at what is called the boiling point. So the temperature gets hot enough to where the water just starts spontaneously going into gas. We start getting all this gas coming out of our boiling pot. And when that's happening, that's called vaporization. We can also have really slow change from liquid to gas. So like if you ever have been outside a couple days after it rains really hard, and there used to be these big puddles in the road, right? Just kind of sitting on the side of the road. And after a day or so, those puddles dry up and disappear. Well, obviously they weren't boiling because it wasn't 200 degrees outside and the water was going straight to gas, but they did evaporate. So evaporation is the slow method for liquid to gas change. And this just means that it's happening over a very long period of time below that boiling point. So the water is not getting super hot and boiling away, but it is just slowly over time changing from liquid to gas. So vaporization, fast change, evaporation, slow change. If we want to take that gas and turn it back down into water, that's called condensation. So condensation is gas to liquid, taking something that's in the air, zooming around as little gas particles and condensing down into a liquid. So this is actually what happens to create clouds and rain. So our atmosphere is full of water vapor. So water that's in a gas form is just kind of floating all around way high up, thousands of feet above the earth. When that water cools down enough in the air, those tiny little water vapor droplets start sticking together and that's what forms clouds. So you see clouds drifting by on a sunny day. That's water that's kind of condensed together up in the atmosphere. Now, if the weather gets even cooler, the water in that cloud can condense so far to where it forms droplets that become too heavy for the air, and they fall to the ground as rain. So condensation is taking something that's a gas, cooling it down to the point where it starts clumping together and forming a liquid. So these are ones that you're probably most familiar with, even if you maybe hadn't heard these exact terms already. If you take a solid, you can melt it to turn it into a liquid. You can take that liquid and vaporize it in order to go to a gas. It can also evaporate. We can take that gas and condense it to go down to a liquid, and then freeze that liquid and turn it into a solid. Now, the ones that you guys might not have heard of before, but to me are some of the coolest ways that matter can change, are what's called sublimation and deposition. This is when we go directly from solid to gas and then back to solid. So sublimation is when we go from a solid form to a gas form. So if you've ever seen dry ice at a party before, where like somebody opens a cooler and all of this kind of foggy smoke starts coming out, that is sublimation. So the ice is not water, it's actually frozen carbon dioxide gas, which means it's super, super, super cold, like negative 200 something degrees Fahrenheit. So when that solid hits the air around you, say 75 degrees, that's over a 200 degree change from the solid to the air. So instead of becoming liquid carbon dioxide, the dry ice just starts immediately boiling and turning into a gas. And so this is called sublimation. When you have something that's an extremely cold solid, we put it somewhere that's relatively extremely hot, and it skips the liquid step entirely and goes straight to gas. Deposition is the opposite way around. We take this gas and we cool it down, chill it down super fast, super cold, and we skip the liquid step entirely again and go straight to solid. So we had these gas particles that were zooming around all around us. We chilled them down really far, they clumped together, and now we have solid where we used to have gas before. So this little chart right here sums it up nicely. We've got sublimation going from solid to gas, and then deposition going back the other way around, gas turning directly into solid. You can also trace the other phase changes that we talked about on this chart. So starting from a solid, we melt to turn into a liquid, and then evaporate or vaporize / boil to go into a gas. We can then condense that gas, turn it into a liquid, and then freeze that liquid and turn it into a solid once more. So those are our phase changes and the terms for how we describe going from solid to liquid to gas to liquid to solid to gas. All right. Any questions about our solids and liquids and gases so far, or about any of those phase change terms?
Nope.
Not so far.
All right, like I said, this first part is pretty simple and straightforward. It uses a lot of stuff that you may have heard before. And so the worksheet, the homework for this is pretty straightforward as well. So for today's assignment, oh wait, hold on, I'm looking at the wrong button. There we go. If we go back to our Google Classroom. There's a worksheet and a form that both are the same thing, where for the first part, you have to label these three pictures as being either a gas or liquid or a solid. So on the worksheet, you can put the labels right underneath, or if you fill out the Google form, you just have to say what's in the left diagram, what's in the middle diagram, and what's in the right diagram. And then the second part of it looks really similar to that triangle that we just saw on the notes, where we have these different labeled arrows on this diagram down here. And you have to label each phase change on the arrow using this diagram. So arrow 1, for example, is whatever you would call going from a gas to a solid. Arrow 5 is whatever you would call going from a liquid to a gas. So that's what you'd write in and your answers down here. All right, any questions about the first part of the notes today, or about the homework, the assignment that I just showed you guys?
No.
No.
So the second part of the notes today are shorter, but a little bit more complicated, which is why I wanted to make sure to go over them before we get to tomorrow, when your assignment that has to do with these notes will be due. So let's take a look at heating curves. All right, so we just talked all about phase changes and how we go from one phase to another and what that's called. Heating curves are a way of showing in a graph what's happening to the matter, to the stuff that's going through a phase change based on the time and the temperature that it's taking to go from one change to another. So these heating curves are also sometimes called phase change curves or phase change diagrams. And like I said, they're a way of showing in like a graph or a figure form what's going on with these phase changes that we just talked about. The melting and the freezing and the boiling, all that good stuff. Hey, Lupita, I see you. Welcome on. So the way that these heating curves work, and I'll show you what they look like in a second, is that they show you the temperature of a certain piece of matter, whether that's ice or metal or air. As we add energy, or in this case, when we say energy, we essentially mean heat, over a period of time. So we start off with something, usually something that's a solid and is very cold, and we add heat to it, and we add more and more and more heat, and see how that changes the temperature of the matter, of the stuff that we're heating up. So there's kind of two different sections of a heating curve. One of the sections has to do with that stuff that we were talking about earlier, kinetic energy. So if you remember from the beginning of the notes that we're looking at, kinetic energy, that KMT, has to do with particles moving. So solids have low kinetic energy because their particles don't move very much. And then liquids have faster particles. And then gases have the fastest ones. And so the kinetic energy of something is essentially a measurement of how fast the particles are moving. And we talked about how when you increase the temperature of matter, that causes the particles to move faster and faster and faster. And so that increases the kinetic energy of that matter. So hotter temperature means faster particles, means more kinetic energy. So we can represent that on, if we take a look at our heating curve. So this is what a heating curve looks like. We have temperature on one side. In this case, since this is a science class, we like to use the metric system. So we measure temperature in degrees Celsius. And down here on the bottom, the x-axis is the amount of time that has passed. So if you imagine at the very start of our heating curve down here, pretend like we have a big block of ice. So this is a heating curve for water that we're looking at. So pretend you have a big block of ice, you stick a thermometer in the top of it, and then put that on a stove that is slowly heating up. Your heating curve, so the temperature of this ice, would look something like this. It would get hotter for a little while, and then the temperature would stay the same for a little while. Then it would get a lot hotter for a while. Then the temperature would stay the same for a while, and then it would start to get hotter again. So this is a classic heating curve. We have these areas where the temperature is going up and up and up. And we have these areas where the temperature is staying the same. So there's the smaller one down here and this bigger one up here. So if we start with a big block of ice that say is at negative 20 degrees Celsius, we increase the temperature of that ice. So it's a solid, right? That's our first state of matter, solid. And since the ice is getting hotter, that means that the kinetic energy is going up, right? Those little ice particles are starting to vibrate faster and faster and faster. Once we hit 0 degrees Celsius, which is the melting point of water, we have a phase change. So we'll talk about it in a little bit more detail in the next part of the notes. But whenever you see these flat areas of the curve, that means that a phase change is going on. So the temperature stops going up for reasons that we'll talk about in a second, right here. And then once our solid has completely turned into a liquid, so once all that ice is melted and turned to liquid water, then the temperature starts going up once again, right? Now we have some water that's sitting on our hot stove, and so that water is going to get hotter and hotter and hotter and hotter. Since the temperature is going up, that means our particles are moving faster. That means our kinetic energy is going up. Finally, that water hits 100 degrees Celsius, which is the boiling point of water. So whenever you have a big pot of water on the stove and you start to see those bubbles coming up and the water vapor boiling off, that means you've hit 100 degrees Celsius. So now we're boiling, we're vaporizing the water. So again, while we're boiling, the temperature stays the same, in this case for a lot longer, because it takes a long time for that water to boil away. But once all that water is boiled, all that you have left in your pot, or essentially in the room, is a whole bunch of gas, right? Now you have all this water vapor that's above your pot in your room. And so if you just leave the stove on, that gas is going to get hotter and hotter once again, because the stove is going to start heating up the gas around it, the air around it. So for a third time, our gas is getting hotter, which means the particles are moving faster, which means that our kinetic energy of the gas is going up. So every time you see these lines going up on a heating curve, this one down here, this one in the middle, and this one up here, that means that we're increasing the temperature and therefore increasing the kinetic energy that's in these little particles that are there. All right. Any questions about the kinetic energy part of the heating curve so far? All right. And as always, if you think of a question that comes up in the middle of me talking, feel free to put it in the chat. So you can type it down in the chat below, and I can get to it when I go on one of these little question breaks right here. All right, so we've talked a lot about these parts of the heating curve where the temperature and the energy is going up, up, up. But what about these flat parts right here? Why is the temperature staying the same? The reason has to do with something called potential energy, or PE. So we talked a lot about kinetic energy just now, how when you have the temperature go up, the particles get faster, and that means more kinetic energy. Potential energy has more to do with when we go through one of those phase changes. When we go from a solid to a liquid and melt, or when we go from a liquid to a gas and vaporize or evaporate. So if the kinetic energy has to do with how fast these particles are moving all around, the potential energy has to do with how tightly the particles are fused together, how tight in together those particles are. So when we go from a solid to a liquid, right, our particles need to get farther apart. Because in a liquid, we have more energy, more kinetic energy, so the particles move around more. And we don't have that set shape, so they can kind of flow around each other and fill up the containers. So as you go from one phase to another, specifically from a solid to a liquid, or from a liquid to a gas, the potential energy is increasing because you're forcing those particles away from each other, right? In a solid, the particles are really tightly packed together. And so you need to force them apart from one another in order to turn that solid into a liquid. So when we're going from a solid to liquid or a liquid to gas, these particles are not moving around any faster than they were a second ago. So that's why the temperature stays the same, stays flat. Instead of all that energy making the particles move faster and faster and faster, instead, the energy is pulling the particles apart from one another. So that's why our temperature and our kinetic energy stay the same while we're going through these phase changes. Because instead of the liquid becoming hotter and hotter and getting more and more movement, instead we're going from a tight together solid to a more loosened up liquid. So the energy from your stove, the heat energy from there, isn't going into actually making the temperature higher. It's going into breaking those particles apart from one another. So that's why those flat parts of the heating curve look the way that they do. So we're not getting any hotter in this area. Instead, what we're doing is melting and going from a solid block of ice to liquid water. When our water is boiling, it's not getting any hotter, so boiling water will always be at right around 100 degrees Celsius, no matter how long it's boiling for. But we're using all of that energy from the stove to increase the potential energy and move those liquid particles farther away from each other until they turn into gas particles. So that's probably the most complex part of the heating curve that I wanted to talk about you guys today, is this idea of these flat parts of the curve exist because we're going through a phase change. We're not making the particles any faster, any hotter. Instead, we're making them just move farther apart from one another. So overall, if we look at the heating curve as kind of everything put together, we start off with our solid block of ice at this very cold temperature down here. It heats up and gets more kinetic energy until it reaches the melting point right here. So for water, that's 0 degrees Celsius. While the water is melting, it stays the same temperature, but we're breaking those particles apart from each other until we form liquid water. Once our ice completely turns into liquid water, that water will then start to get hotter and hotter and hotter until it reaches the boiling point or the vaporizing point, which again, for water, is 100 degrees Celsius. Once that point is reached, we start turning that water into a gas, into water vapor. So the temperature stops going up at that point because we are boiling that water away. We're using all that potential energy, forcing the particles away from each other, but not necessarily making them any hotter. Finally, once we've reached the point where the water is all boiled away, the burner on your stove is just going to heat up the water vapor in the air around you, causing that gaseous water to move faster and faster and faster. So that's how these heating curves work. You have these areas where the temperature is getting hotter because we're stuck in one phase and we're just getting warmer and warmer. And then you have these flat areas where the temperature stops going up because our matter is changing from one phase to another. It's not getting hotter, it's going through a change which stops the temperature from rising. All right, hi Levita. So, questions on the heating curve and what's going on in there? All right, does all of that mostly make sense to everybody?
Yes.
You're still muted. I can't hear you.
Yes.
Still muted. There you go. You got it.
You want to work this.
Yeah, it can be touchy sometimes. All right, so how do we feel about the heating curve? Kind of, sort of makes sense. Want one more walkthrough? You can go ahead and ask, it's okay.
Can you do a quick walkthrough? Because I had to step away for a second.
Yeah, sure thing.
I'm sorry if anybody's.
No worries, that's what we're here for. All right, so we have this line here, and this represents the temperature of, in this case, water, as we take it from a solid block of ice and heat it all the way to where it boils away into gas. And so we've got these parts of the graph that go up, right? There's this part down here, and this part in the middle, and this part at the end. So that's where the temperature is rising. And the temperature is rising because we essentially have this big block of ice that's on like a stove, a hot stove. And so the ice will start to heat up until it changes into water. And then our water will heat up until it starts boiling into a gas. And then once all the water is boiled away, the gas that's around the burner will start heating up. So that's what's going on in these sections that are rising. We are in one state of matter. We're either a solid, a liquid, or a gas, and we're getting hotter. These flat sections right here on the bottom and the top are where we're not getting hotter, but we're changing from one state into another. So the temperature stays the same, but at the start, we're a solid, we're a block of ice, and at the end of this section, we're water, we're liquid. Same thing with the top line up here. At the start of this section, we are liquid water, and then by the end of it, it's all boiled away and turned into gas. So that's why these lines are flat and the temperature is not going up, because we're changing from one form to another. So down here, we're changing from solid to liquid, and then up here, we're changing from liquid to gas at the end. So we start as a solid block of ice. That ice heats up until it starts melting. Then the temperature stops going up, but we melt all of that ice from a solid to a liquid water. Then once it's all water, the temperature starts going up again. So now we're a liquid until we reach this temperature up here. This is where our water starts boiling. And so now the temperature stops going up because we're boiling our water and slowly over a long period of time, turning all of that water into gas. And then once the water is all boiled away, we'll start heating up the gas that is in the pot, the gas that's left over, essentially. So we're going up in temperature when we're heating up one phase, and we stay the same in temperature when we're changing from one phase to another. All right, a little bit better. And so hopefully, so again, those notes are posted up on the Google Classroom. You can go back and look at that diagram at any time that you want. And you'll probably find that helpful for the daily assignment that's going up tomorrow, which I will show you here in just a second. So again, earlier today, we went through some basic notes on the states of matter and phase changes that you can go back and look at. And then today's assignment is to finish this quick little worksheet on the different states of matter, solids, liquids, and gases, and what it's called when we go between them. Wednesday's assignment has to do with the heating curve. And so I've given you guys a kind of very generic heating curve that looks like this. Again, should look pretty similar to what we were just looking at. And there are a series of questions underneath that are basically asking about what's happening at different point of this heating curve. So this is specifically, like we were just talking about, a heating curve of water, so an ice cube that you're measuring. And so down here, the questions are things like, what's happening in between A and B? What is the state of this matter? So is it a solid, liquid, or a gas if we're between C and D? So those are the kind of questions that you'll be asking, or you'll be answering about our labeled heating curve right here. So again, if you go back to the notes that we were just looking at and that are posted on the Google Classroom, then hopefully you should be able to find those answers pretty easily. All right. So that's pretty much it in terms of the notes that I want to make sure to cover with you guys today. And a little bit about the assignments for today and tomorrow. Any final questions about any of the things that we talked about today? And Lupita, I am recording this video and I recorded the notes that I went over earlier. So if you want to go back and watch me go through those while you're going with them on your own, then you'll be more than welcome to. I'll be posting that up as soon as I'm able to upload it today. So before we finish up here, are there any final questions about states of matter, phase changes, or reading a heating curve? All righty, if not, let me stop this recording.